Sheet 2 on you. Sheet 3. Sheet 3. Have you looked into the first problem? Have you solved the first problem? Okay. Alright, so this is a solid cylinder, radius r, and it rests on a rough surface, and the coefficient of friction is mu equal to 1 between the cylinder and the surface, and the block itself rests on a smooth surface. Their masses are known, and the arrangement passes over a pulley like this. Now a force F is applied, F is applied at the point P of the cylinder in a manner that the cylinder rolls over the surface. Now, as you go on increasing the value of F, the propensity for the cylinder to slip over the surface would grow, right? So what's sought in this problem is the maximum permissible value of F applied at the point P at a distance 2r by 3 from the center of mass, so that it still rolls over the surface, right? That's what's required in the problem. Now, let's have a question. Let's draw the free body diagram of both the cylinder and the block and write down the equations of translation and rotation, and then also write down the condition for rolling, right? These are the things that are involved. Conditions for translation and rotation for this, condition for translation of this, and constraints, if any, which includes the rolling constraint. Okay. Now, as far as the cylinder is concerned, since it rolls over the surface, the frictional force between the cylinder and the surface is static in character. It has to be less than mu times n. N is the normal reaction, mu times n between, right? And that would determine the limiting value of F. Eventually, that would determine the limiting value of capital. Now, right away, we're not sure as to the direction of static friction. Right away, we are not sure as to the direction of static friction at this point of contact. Like I said, you can get indiscriminate about that selection. You can choose any one direction as the direction of static friction. Go ahead and write your equations commensurate with that direction. The sign that emerges will tell you whether your chosen direction was right or the actual direction is opposite to the chosen one, right? So, let's say on this cylinder, static friction acts on the right, on the left, sorry. So, for the cylinder, the forces are F at a distance 2r by 3. Then I am assuming static friction that the block exerts on the cylinder is leftwards. F. We do not know the magnitude of F. All that we know is it has to be less than mu n. And there is tension acting rightwards. There is tension acting rightwards through the center of mass. Then of course, ornamental forces which will not interfere with our calculations, mg downwards, and there is normal reaction from the block upwards. There is normal reaction from the block, well, in absence of a vertical acceleration, n will be equal to mg in this case. Now, under the influence of the horizontal forces, the cylinder experiences a leftward acceleration ACM. And let's say an angular acceleration alpha because of the torque about the center of mass. Say F exerts about the center of mass an anti-clockwise torque, small f exerts a clockwise torque, and let me assume that the net torque is anti-clockwise. That's all right. No issues with that, right? Eventually, alpha will also come married with a sign, right? Does this summarize all the forces acting on the cylinder? So, are we ready to write down the relevant equations for the cylinder, right? Also realize that the ICM of the cylinder is half mr squared, right? So, equation for translation for the cylinder. F plus small f minus t is MACM. How about it? F plus small f minus t is MACM, right? Then take torque about the center of mass. Take torque about the center of mass. By the way, now my question also is, could I have taken torque about the point of contact in this case? This is not a point which is at rest. It has a velocity same as that of the block. So I couldn't have taken torque about this point because this is not the instantaneous center if this is a movable surface, right? This point has the same velocity at any given instant of time as the velocity of the block. This is not an eligible point towards applying tau equal to I alpha. But then center of mass always is, right? So then if I take torque about the center of mass, then I have F into 2r by 3 anti-clockwise minus small f into capital R clockwise T produces no torque about the center of mass, and that must be equal to half mr squared into alpha. F into 2r by 3 minus small f into r is half mr squared into alpha. Now, this is all that we could do as far as the cylinder is concerned. Clear? Let's come to the block side of this story. The block now. Let's look at the block. For the block, of course, there is tension T acting to the right. The block exerts on the cylinder a frictional force F to the left. So the cylinder will exert on the block a frictional force F to the right. Then there is weight of the block acting downwards. If the block exerts on the cylinder a normal reaction upwards, the cylinder will exert on the block a normal reaction N downwards, and the ground will exert a normal reaction, say N1 on the cylinder. Is this all as far as the cylinder is concerned? Right? Right? No? Now, realize that the amount by which this point moves to the right on the cylinder is the amount by which the center of mass of this moves to the left. So if the center of mass has an acceleration ACM to the left, then this will have an ACM to the right. That's a string constraint. That's a string constraint. Yes or no? So then, under the influence of these forces, this has an ACM to the right. This has an ACM to the right. We are ready to write down the equations of motion for this. In fact, only one equation of translation is all that we need to designate here. So we have T plus F is 3m into ACM. That's for the block. That's for the block. One condition is still pending. We have not yet deployed rolling criteria. We have not yet deployed rolling criteria. Now, look, as far as the cylinder is concerned, we have chosen ACM as the acceleration of the center of mass of the cylinder to the left, and we have chosen alpha this way. Right? Now, observe the point of contact. This is the point of contact. The point of contact has a R alpha to the right because of tangential. Imagine it to be in a state of pure rotation with angular acceleration alpha. And it's going to have R alpha rightwards and it's going to have ACM leftwards, superimposing pure translation with pure rotation, right? ACM leftwards. And that leads to R alpha minus ACM as the net velocity of the point of contact to the right, right? So then R alpha minus ACM is the net acceleration of the point of contact to the right, and that must be equal to the acceleration of the block to the right, right? Rolling would mean the acceleration of the point of contact must be the same as the acceleration of the block. The acceleration of the block is ACM to the right. So then this must be equal to ACM, right? Yes or no? Which gives us R alpha is 2 ACM, which gives us R alpha as 2 ACM, yes or no? Now, let me remove the clutter from here and leave the equations behind and deal with the equations because all the physics is set here. The objective now is to solve for small f. To solve for small f in terms of capital F. The objective now is, the algebraic objective is to solve for the frictional force, static friction small f in terms of capital F. Once having done so, call small f less than or equal to mu mg, and that will give me capital F less than or equal to something. And when I get capital F less than or equal to something, then that something would be the maximum permissible value of capital F. Right? This is what we want to do. In equation 2, you could just do some tweaking. This R would get cancelled with this R. get cancelled with this R. First thing, let me get rid of alpha, which appears only here, right? And this R alpha I can write as 2ACM. This R alpha I can write as 2ACM, yes or no? So then this equation 2 could be rewritten as 2F by 3 minus small f, and write this R alpha as 2ACM. So this will become MACM. This will become MACM. Now, if I add equations 1 and 3, T gets eliminated. Do you realize that? If I add equations 1 and 3, T gets automatically eliminated. So I end up getting capital F plus 2F is 4 MACM. Yes or no? Right? This is adding 1 and 3. ACM also I don't need. I divide these two. I divide these two, or I can say F plus 2F is 4 times MACM. That means 4 times 2F by 3 minus F is what I get. F plus 2F is 4 times this number, but this number is 2F by 3 minus F. Clear? So when I transpose 5F by 3 equals 3F. Right? So I get small f as 5F by 18. So since f turns out to be positive, means the chosen direction is appropriate. If you had chosen the direction opposite, then you would have got f equal to minus 5F by 18. Right? And this f, since it's static friction, it has to be less than or equal to mu times mg. Right? Which leads to f less than or equal to 18 mu mg by 5. So the maximum f is 18 mu mg by 5. Does it match? Mu mg. It has to be mg, otherwise, see, dimensionally it will not be correct. Mu g would be acceleration. There has to be an m, otherwise there would be dimensional inconsistency. See, the ideas are very simple. We applied translation and rotation to the cylinder. We applied translation to the block. We applied the string constraint, and that appeared as acceleration of the block to the right equal to acceleration of the center of mass of the cylinder to the left. And then the last bit was to write down this rolling condition. And then the rest was ordinary algebra. We solved for small f in terms of capital F. Since we assumed rolling to take place, this couldn't have exceeded mu mg, giving us the largest possible value of capital F, the externally applied force applied at a height 2h by 3 from the, or 2r by 3 from the center. Got me? Can I wipe this off? Again, realize it was so easy. I mean, it's just that there were more number of equations, but then there's nothing difficult about it. So we have this solid sphere which is spun with an angular velocity omega naught and is gently placed on a rough movable surface having coefficient of friction mu, and they have the same masses, and we'll assume that the whole thing is long enough for the ball to never leave the surface. All right. We want to find the distance covered by the plank. We want to find the distance covered by the plank in a time, where this starts to roll. Eventually it will start rolling on the surface. Okay. Let's put together all the forces for the sphere and the block in perspective and see what's happening here. First things first, initially when it's set into rolling, this point on the sphere has a leftward velocity r omega naught, right? Whereas the corresponding point on the block has zero velocity. So there would be a slipping condition prevalent here. To begin with, there would be a slipping condition on the block prevalent, and the block, since it witnesses at the lowest point a leftward velocity, it will exert on the sphere a rightward frictional force, and frictional force would be approximately maximum static, mu mg approximately, right? And the sphere in turn would exert on the block a leftward frictional force as a reactionary measure, right? So for the block then, for the sphere, forces act. Well, there is frictional force, it's not static, it's going to be kinetic, approximately maximum static. Frictional force F in this case is rightwards, and the direction I told you why it's going to be rightwards on the sphere. I hope all of you understand why it's going to be rightwards on the sphere. There is obviously going to be mg downwards, there is going to be normal reaction upwards, right? Does it summarize all forces acting on the sphere? It does. Now, under the influence of this force, the center of mass of the sphere would have an acceleration which would be mu g. The center of mass of the sphere would have an acceleration mu g. Force divided by mass, mu mg divided by m, is going to have a rightward acceleration mu g. Now, not only that, this frictional force acting to the right will produce an anti-clockwise torque, about the center of mass, leading to an anti-clockwise alpha. That will cause an anti-clockwise alpha, yes or no? This anti-clockwise alpha will kill omega, whereas this mu g will build up, VCM will build up, VCM over a period of time. Now, t seconds later, say rolling commences t seconds later. In t seconds. So t seconds later, the velocity of the center of mass of the sphere is going to be, t seconds later, the velocity of the center of mass of the sphere is going to be initial velocity of the center of mass, which is 0, plus at is mu g. Mu g t would be the velocity of the center of mass of the sphere t seconds later. Clear? To the right? No? V is u plus at. The angular acceleration on the sphere, in this case retardation, is going to be torque about the center of mass, mu mg into r divided by I about the center of mass. I about the center of mass is going to be 2/5 mr square. That's angular retardation produced. Yes or no? Which is going to be 5 mu g by 2r. That's angular retardation. And therefore, the omega t seconds later, there is a VCM like this, and instead of omega naught, let's say it becomes omega t seconds later, angular velocity becomes omega. So omega is going to be initial omega, which is omega naught minus alpha t. Omega would be omega naught minus alpha t. Alpha, which is 5 mu g by 2r into t. VCM mu gt, omega is this, right? Now, for the sphere, for the block, t seconds later, what transpires on the block? This is the block, mass m. The block exerts on the sphere kinetic friction mu mg to the right. Sphere will exert on the block mu mg to the left. Right? So the block will have a leftward acceleration, mu g will have a leftward acceleration, mu j. T seconds later, the velocity of the block t seconds later, when rolling starts, the velocity of the block would be mu gt, yes or no? V equal to u plus at, and leftwards, right? This is all that we could do for the block. One last condition pending is rolling condition. Rolling condition in the tth second when it happens, right? Look, in time at an instant t, this has a velocity VCM which we have computed to the right. It has an omega this way, and therefore it has r omega because of pure rotation leftwards, and it has VCM rightwards. This is the state of the point of contact on the sphere, and this point of contact must have the same velocity as the block to the left, so its velocity must be Vb to the left, which means rolling requirement would imply r omega minus VCM equal to Vb. R omega minus VCM equal to Vb. That's going to be the rolling requirement. Clear? R omega minus VCM equal to Vb, and R omega, as you can see, is omega naught R minus 5 mu g by 2t, right? R omega from here multiply by R omega is going to be omega naught R minus 5 mu g by 2 into t, that's R omega, and VCM is mu gt, VCM is mu gt, equal to Vb. Vb is mu gt. Vb is mu gt. See, you can solve for t from this. So in t seconds, which is obtained from here in this equation directly, you know the time it takes for rolling to commence. You would know the time it takes for rolling to commence. Now, look at the block side of the story. In t seconds, which is obtained from here, the distance covered by the block would be half of AB, which is mu g, into t squared. That's going to be the distance covered by the block to the left in t seconds when rolling starts, and t is known directly from here. Got me? Is that all right? Have you attempted 3? Not yet, no? All right. So problem 3. All right. So we have this cylinder and this plank and an external force acting on the plank at an angle theta. And the cylinder rolls on the surface. There is no slipping anywhere. So given this, we want to find the frictional force at A and B, and also the acceleration of the center of mass of the cylinder. Acceleration of the center of mass of the cylinder. These are the two things that we are seeking in the problem. So we need to draw the free body diagrams first of the cylinder and the plank. Write down the equations of motion, constraints if any. Right? So for the cylinder, now frictional force at A and B would be static. Right? Would be static. Don't care about the direction, select your directions randomly, does not matter, right? So, say frictional force at A acting on the cylinder is F1, at B it's F2. Under the influence of these forces, say the acceleration of the cylinder is ACM, the acceleration of the cylinder is ACM, and let's say the angular acceleration is alpha. Alright, and of course there is normal reaction from the plank, there is weight of the cylinder downwards and normal reaction from the ground. But I am not representing those forces because they will have no role to play in the overall scheme of things here. Okay. So equation of motion for the cylinder, for translation what would it be? F1 plus F2 is MACM. Then F1 into R minus F2 into R is ICM alpha, right? ICM, which is half mr squared into alpha. If you look at the point of contact, it has an acceleration ACM to the right because of pure translation, because of pure rotation, R alpha to the left. So ACM must be equal to R alpha. That's the rolling on this surface, that's the rolling condition on this surface. So what I can do is ACM equal to R alpha, I can use right away in this, right? This R alpha I can write as ACM. So this is half MACM, right? If I add these two, then I get 2 F1 is 3 by 2 MACM. So F1 then becomes 3 by 4 MACM, and F2 then would become 1 by 4 MACM, right? So I know F1 and F2 in terms of ACM. I know F1 and F2 in terms of ACM. Okay. Now the objective is to find ACM. To find ACM, I'll have to look at the plank. Now I'll have to look at the Planck side of the story. So as far as the Planck is concerned, there is F cos theta horizontal, F sin theta vertical, right? Then of course there is mg acting downwards, normal reaction upwards. If I have chosen the Planck to exert a frictional force on the cylinder F1 to the right, the cylinder will exert a frictional force F1 to the left on the Planck. Right? Now look at the point A on the Planck. The point A on the Planck will have the same acceleration as the point A on the cylinder, For the point A on the cylinder, look, because of pure rotation, pure translation, it's going to have an ACM, and because of pure translation about the center of mass, R alpha, but R alpha is ACM, so it's going to be 2 ACM. It's going to be 2 ACM. So the acceleration of the Planck is going to be 2 ACM, right? So then we get F cos theta minus F1 is mass into acceleration of this point is 2 ACM. Small m in this case, small m. The Planck is small m and the cylinder is capital M. And all that you need to do is F1 is 1/4 MACM. You could plug in right here and solve for ACM. Got it? This is it. Was it difficult? Have you attempted the next problem? No? Sphere. So we have this sphere. Initially it has a velocity v naught downwards and an angular spin omega naught as shown, right? We want to be able to discover the condition for which, well, for the time being it's moving down. You realize that it's moving down? I mean, its direction of motion would be solely determined by VCM, not by omega, right? So we want this to come back to the state. First of all, forces acting on this. Well, there is like mg cos theta this way. There is mg sin theta like this. And there is frictional force this way. Now, The velocity of the lowermost point, as you can see, is at this instant is V naught plus R omega naught to the left. And that's the reason frictional force will act upwards. And this frictional force is going to be kinetic friction because there is rubbing actually at this point. So this is going to be mu mg cos theta, and of course there is normal reaction n like this. So this frictional force is mu mg cos theta, right? Now, mu greater than tan theta means mu cos theta greater than mg sin theta, mu g cos theta greater than mg sin theta, mu mg cos theta greater than mg sin theta. And if mu mg greater than mg sin theta means frictional force is larger than mg sin theta, that means VCM will decrease, it's going to retard, right? Now, eventually, VCM will decrease, omega will also decrease because this friction will produce a retarding torque, okay. Now, after a while, when it descends down and VCM becomes 0 and VCM becomes 0 and omega naught is still not 0, is some omega naught is some omega, right? It will not go down further. Do you realize it will not go down further? At this point, the velocity of this point would be r omega downwards, and therefore frictional force will act upwards and will bring it back to the original point. This frictional force upwards will carry the center of mass to where it started. So the important thing is, at an instant of time t when VCM becomes 0, omega should still be greater than 0. That's the physical condition to be deployed. Okay. So let's find out the time t in which VCM becomes 0. Let's find the time t in which VCM becomes 0. Realize that VCM becomes 0 in t seconds. Initial VCM is V naught, right, minus the retardation, which is mu g cos theta minus g sin theta. That's a retardation, yes or no? What's the force in the upward direction? Mu mg cos theta minus mg sin theta. So the acceleration in the upward direction is mu g cos theta minus g sin theta. But acceleration upwards is the retardation here. So mu g cos theta minus g sin theta into t. So you know the time t in which the velocity of the center of mass becomes 0. Right? Now, in this time t, what happens to omega? Omega should be greater than 0. So first we want to find alpha, the angular retardation. That's going to be the torque about the center of mass, which is mu mg cos theta divided by I of the sphere about the center of mass, which is 2/5 mr squared, Sorry, into r, right. So that makes it 5 mu g cos theta by 2r. 5 mu g cos theta by 2r, right? That's the angular retardation. So in t seconds, angular velocity omega should be greater than 0. That's the only condition. So in t seconds, what's omega? Omega is going to be initial omega, which is omega naught, minus alpha t, which is 5 mu g by 2r cos theta into t. That must be greater than 0, where this t can be replaced by v naught by mu cos theta minus sin theta into g. So replace this t by this and say omega naught greater than this number. That's a required condition. Omega naught greater than this number, where t could be replaced by that expression. Right? That's a condition so that it could, and see if omega is still greater than 0, the velocity of this point is downwards, Point of contact, frictional force will act upwards, it will accelerate the center of mass upwards, and the sphere will come back to this original state. Right? All right. See what's happening here. Just before impact, this is the state of the ball. V downwards and omega like this. V downwards and omega like this. Just after impact, it's given that this V becomes V by 2. And we need to find what happens to omega. Let's say omega becomes omega prime. Now, what's the physics working in the problem? Let's see. Let's look at the physics working in the problem. When the ball hits the ground exerts an impulsive force N, up, right? And this N acts for a short time delta t to produce a linear impulse J. So there is a linear impulse J, which is the normal force from the ground, which is high in magnitude because it's a case of collision, acting for a very short time delta t, producing a linear impulse J upwards. Now, what does this upward linear impulse do? Linear impulse means change in linear momentum in the upward direction. So, final linear momentum in the upward direction minus initial linear momentum in the upward direction. Final linear momentum in the upward direction is mv by 2. Initial linear momentum in the upward direction is minus mv. You know what I'm saying? So, linear impulse in the upward direction is final linear momentum in the upward direction minus initial linear momentum in the upward direction. Initial linear momentum is mv in the downward direction, or that's the same as minus mv in the upward direction. So, change in linear momentum in the upward direction is the linear impulse in the upward direction. So, that makes it 3 mv by 2. Right? That makes it 3 mv by 2. Now, because of this N, there is a frictional force mu N acting for a short time. There is a frictional force mu N, right? Because this point has a leftward velocity r omega like this, because of which a frictional force mu N would act to the right during collision. And this mu N also acts for a short time delta t, right? So that's impulse because of the frictional force. Mu J becomes the frictional impulse, right? This becomes a frictional impulse, yes or no? Right? Mu J is the impulse of the frictional force, right? J is the impulse of the normal force, mu j is the impulse of the frictional force. Now, this impulse mu j in this direction produces an angular impulse. I have discussed angular impulse, right? Produces an angular impulse mu j into r. Produces an angular impulse in the anticlockwise sense. Mu j acting like this, frictional impulse, produces an angular impulse about the center of mass. Mu j into r is the angular impulse about the center of mass. Yes or no? In the anticlockwise direction. Angular impulse in the anticlockwise direction would be final angular momentum in the anticlockwise direction minus initial angular momentum in the anticlockwise direction. So, angular impulse about the center of mass is mu j into r, mu j into r, which will be final angular momentum. This will be about the center of mass anticlockwise, right? This is mu j into r is anticlockwise. That's final angular momentum in the anticlockwise direction minus initial angular momentum in the anticlockwise direction. Now, what's the final angular momentum in the clockwise direction? ICM omega prime in the clockwise sense. So, what's the final angular momentum in the anticlockwise sense? Minus ICM omega prime. So, minus ICM omega prime is the final angular momentum in the anticlockwise direction minus initial angular momentum in the anticlockwise direction would be minus ICM omega, right? So, minus of minus ICM omega. Yes or no? Final anticlockwise angular momentum minus initial anticlockwise angular momentum. That's the angular impulse anticlockwise about the center of mass. So, which is like ICM into omega minus omega prime. ICM you know is 2/5 mr squared. J we already know is 3 mv by 2. This J you can plug in as 3 mv by 2. Mu is known. So, you can solve for omega prime. You can solve for omega prime. Okay, write down. Couldn't get all the problems typed yesterday, so I'll dictate. Write down. So we did how many problems here? 5 problems. So maybe the 6th problem. Please write down. A solid cube of wood of side 2A and mass capital M. A solid cube of wood of side 2A and mass capital M rests on a horizontal surface. Rests on a horizontal surface. The cube is constrained. The cube is constrained to rotate about an axis. To rotate about an axis passing through D. Passing through D. and perpendicular to the face ABCD, and perpendicular to the face ABCD. That means this, see, this is an axis passing through D and perpendicular to the plane of ABCD. A particle of mass small m strikes AB normally, with a velocity v as shown, Assume small m much smaller than capital M. Assume small m much smaller than capital M. And also small m gets embedded into capital M after the impact. Also small m gets embedded into capital M after the impact. Find the minimum value of V, to topple the cube, about D, okay. Now just a few quick things. For a cube 2a by 2a by 2a, this is the center of mass. I about this axis is going to be 1/12 m 2a squared plus 2a squared. 1/12 m about this axis, see, center of mass axis perpendicular to this, 1/12 m ICM, and perpendicular to this is 1/12 m 1 square plus the other side squared, 2a squared plus 2a squared. That's one thing. That's about this axis, right? Now, so essentially, the principles that you would deploy to solve this problem, right after this impact, you would expect the cube to rotate about D with an angular velocity omega, right? So to find this omega, you might want to apply the law of conservation of, about what point? About D. For the particle and the block system, apply conservation of angular momentum about. Now when small m gets embedded into capital M, since small m is much smaller, I about Cm will remain the same, will not change much, right? And I about D can be found with the help of parallel axis theorem, right? I about D is going to be I about Cm plus this square, m into this square, right? So first of all, you are going to apply conservation of angular momentum, but can you apply conservation of energy before and after collision? Why? No. Why can't you apply conservation of energy? Yes, if small m gets embedded into capital M, it's a perfectly inelastic collision, right? So energy is not conserved, right? So you can't apply, but you can apply conservation of angular momentum, right? You might want to apply that about D and solve for omega, right? Now once this starts to tilt, from that point onwards there is no more collision. So the square, that the cube that originally was hinged at D would now begin to tilt, You would then expect after a while, this had omega initially, after a while the cube might come to a state where, see, this was the original center of mass of the cube, at a height a from the base. Now it will come to a height which is, see, this length is 2a root 2, so a root 2, a root 2. So it will come to a height a root 2 above the ground. Now if the cube somehow reaches this state, then it will completely topple. Do you realize that? If the cube somehow reaches this vertical state where the center of mass is a root 2 above the ground, right, then slightly more and it will tilt, topple, it will completely topple. So it's enough that from this state to this state, the cube is brought. That means this entire half I about d into omega squared gets converted into additional potential energy, which would be mg into this length minus this length would be the gain of potential energy. And where does it come from? Half id omega squared, because between this state and this state energy can be conserved, right? So apply these principles and solve the problem. Please do that, all of you. You might, I'll just dictate another problem because I know you. Problem 7. Can I wipe this off? In the arrangement shown, write down, in the arrangement shown, the rod is freely pivoted at O, the rod is freely pivoted at O and is in contact with a block, this is the block, which moves on the horizontal frictionless ground, having a velocity v at some instant shown, Find the angular velocity of the rod, in terms of theta, find the angular velocity of the rod in terms of theta. Have these two problems. All right. So right after collision, the mass plus the block start to swivel about d. Develop an angular velocity omega about d, right? If it topples about d, means it would be in a state of pure rotation about g, right? Okay. So naturally, the only forces are the impulsive forces that the particle and the block exert on each other, and the angular impulse of the system about any point would be 0, and therefore the angular momentum would be preserved. So angular momentum about d initially is mv into 4a by 3 is the angular momentum initially just before collision, and just after collision it's like a mass m, small m is very small, so it's like I about g into omega. That's the angular momentum in pure rotation, right? I about the axis of rotation into omega. So it's I about d into omega, and easy to calculate I about d because realize that this is a root 2, this is a root 2. I about this axis would be I about the CM axis plus m into a by a root 2 squared, right? So I about d would be 1/12 m 4a squared plus 4a squared 2a whole squared 2a whole squared plus m into a root 2 squared, right? Parallel axis theorem, that's I about this axis obtained from parallel axis. This is I about CM, right? Now, after collision, and what I couldn't have done is, if I said half mv squared is half id omega squared, that would have been wrong. If I had said half mv squared is half id omega squared, that would have been incorrect because during collision energy would have been lost. So half id omega squared is actually less than half mv squared, right? So energy cannot be conserved before and after collision. But once the collision has occurred and it starts to rotate about d, then of course there are no more dissipative forces, and energy can then be conserved. So starting from this state where it started to swivel with an angular velocity omega about d, the center of mass is at a height a, right? And if it could be just about brought to this position, if it could rotate to the extent that it could just be brought to this state, where the center of mass is at an elevation a root 2, then of course it will complete detoppling. Then it will complete detoppling. So then between these two states, I can conserve energy. The total energy in pure rotation here is half id omega squared, right? And that must go towards gain of potential energy, which would be capital Mg into a root 2 minus a. Right? So the omega that you obtain from here can be plugged into this. The omega that you obtain from here could be plugged into this, and the V can be solved for. Is clear? Okay. So this block is moved to the right, and this will fall down. So it's pivoted about a, theta will change with time, and therefore there is an angular velocity associated with OB, which is d theta dt, or its magnitude will be a measure of the angular velocity of the rod. Now if this is h and say this is x, right, then x very clearly is h cot theta. X is h cot theta, yes or no? X is h cot theta. If I differentiate both sides with respect to time, then I get dx dt is h minus cosec square theta d theta dt, right? Hey, but what's dx dt? V. Dx dt is V. So d theta dt is V sine square theta by h, with a minus sign means theta is decreasing with time. That's why you're getting d theta dt as negative. If you take its magnitude, that will give you the magnitude of the angular velocity omega. So this or its magnitude will give me omega. Right? There is another way you could look at the whole thing. This is one thing. What you could do is, look, this point A is in contact with this, right? This is the common normal. This is the common normal. If they have to maintain contact, the velocity of A in this direction and the velocity of the cube in this direction must be the same. Realize that. Now this angle is theta. This cube has a velocity horizontally v to the right, and its component in this direction along the common normal direction is v sine theta. So the velocity of A perpendicular to the rod is v sine theta, yes or no? You realize that? So now look at the rod O A. This point A has a velocity v sine theta, and this length is L. In fact, this length is h by sine theta. H cosec theta is this length. So this is h cosec theta. Right? So now on a rigid body, velocity of this point is 0. Velocity of this point perpendicular is v sine theta. So then the omega of the rigid body is what? Relative velocity of any two points in a direction perpendicular to the line joining them, which is v sine theta, divided by the separation, which is h cosec theta. That's the omega, right? That's another way you could look at it. Got me? How many of you could solve both problems? This last two problems. Okay, the one prior to this one and this one. How many of you could solve this one? Okay, you could solve this one. Huh? You differentiated? Okay, good. By no means am I claiming that all that was to be done is done in rotational mechanics. It can go on forever. I mean, ideally, if it was not the burden of an exam hovering over us, I would want to teach you rotational mechanics for a few years and still think it's not complete. It's really an ocean. But I'm very hopeful that I'll be able to come back to rotational mechanics at a later point of time when